Okay, this is 5.2 and 5.3 homework. The first problem gives us a function, a log function. It says give the domain a range. I know this is really tricky, but we know that exponential functions look like this. Okay? Log functions then are reflections over the line y equals x. So log functions actually look like this. Now this one's been shifted around, right? It's been shifted and stretched and actually reflected as well. So what we can do actually is we can do this. I think it's actually better algebraically to look at this. So what we can do is change this into exponential form. So we can do, I'm going to call this y, and I'm going to do 9 to the y equals. So this would be 9 to the y equals 8 minus 4x. So we do base to the exponent equals the argument. So you have to know how to change into exponential form. Now, once you're in an exponential form, it's easy to see that basically this right here has to be positive. This has to be positive. And it can't even be 0. The reason why is because there's nothing I can raise 9 to get a negative number or to even get 0. So basically I'm going to take 8 minus 4x, I'm going to set it greater than or equal to 0. I'm going to subtract 8. And I'm going to divide by negative 4. And you get x is less than, you have to switch the sign, 2. So x is less than 2 means that I'm going to do negative infinity to 2, not including either. That's interval notation for the same exact inequality. All the numbers between negative infinity and 2, or all the numbers less than 2. Now the range is always all real numbers for these logs, always, because we talked about exponentials look like this and logs look like this. Turns out they keep going up forever. They keep going out to the right forever and up, and they keep going down to negative infinity. So they go down and up. The range is always going to be all real numbers for these. Okay, so the next problem 2 says find the hydrogen ion concentration for apples with a pH of 4.5. So we're told that the pH is 4.5. I'm going to plug that in for pH. And here's the relationship between pH and hydrogen ion concentration. Because all pH is however many hydrogen ions you have that affects the pH. But it's a logarithmic relationship. So if we have this equation, we can solve this. What I'm going to do is multiply both sides by a -1. And then I'm going to change from log form into exponential form. So I'm going to do base to the exponent equals the argument. So it's 10 to the negative 4.5 equals the hydrogen ion concentration. Okay, so all I did was, you can make the circle if you want. It's just base to the exponent equals the argument. And those rules are on your formula sheet as well. But once you have this, there's your answer. It's 10 to the negative 4.5. You can probably put that in as is, or you can do it in your calculator. This is the same thing if you do this in your calculator. You'd obviously round it to this decimal here. That probably will work as well. Okay, the next question says you wish to graph the following relationship on a standard piece of paper. The number of diamonds owned by 20 people, one whom is a billionaire. Okay, well, if you were to graph this, you have people here. So you have person 1, person 2, and so on. And this is on this axis the number of diamonds. Now, most of this is going to be linear. So you're going to have these people own about the same number of diamonds for the most part, except for that billionaire probably owns more diamonds. That number's way up there. So whoever that billionaire is, wherever we graph that point's going to be an outlier. And we can, represent that different ways. But I would say linear for this because most people probably own about the same number of diamonds. But keep in mind that, if you had varying degrees of socioeconomic status, if you have a millionaire, a billionaire, and so on, then you probably want to use logarithmic because the data would look something like this. And in which case you'd want to, bring this axis down essentially to make it more linear. So I don't know if that makes any sense, but you basically use logarithmic scales when the data is really, really spread out like this. And to make it fit on an axis that you can actually see, and to make it more linear, we would then use a logarithmic scale over here where you go 10, 100, 1,000, 10,000. You go by multiplying tens instead of by a linear scale. So that's what that means. Here's another problem about domain. And I know these are tough. But this says base A here. I'm going to call this g of x. I'm going to call it y. And I'm going to change it in exponential form. So a to the y equals x squared minus 9. Now, this is the same thing but written in exponential form. I know that there's nothing I can raise this base to, this base A, there's no number I can raise it to get a negative or to even get 0. So basically, when this x squared minus 9 has to be greater than 0. And I can then add 9 to both sides and have x squared is greater than 9. Square root both sides, and I get x is greater than 3, or x is less than negative 3. And so that's what goes here, negative 3. This interval right here can be represented in interval notation, negative infinity to negative 3. And this interval right here can be represented right here if I go 3 to a positive infinity in interval notation. Okay, the next question wants us to evaluate these log expressions. The key to this is to call this equal to something like x and put it in exponential form. So an exponential form would be 4 to the x equals 4 to the 14th. So you don't need a calculator for this, and I would put this on a no calculator portion of the test because you can see the answer here for x is really 14. So when you write this in exponential form, you see that when you compare, x is 14. Okay, same thing with the next one. Call it something, I'll call it y in this case. And I can write 2 to the y equals 8. Well, 8 is really 2 cubed, so y must be 3. So what that means is this thing equals 3. All right, same thing for the next one. Call it equal to something like z. It doesn't matter, or x, whatever variable you want to use. You have 5 to the x equals 125 in exponential form, but 125 is just 5 cubed, so x is 3. And then the same thing for the next one. When you have, call this equal to something like x, you have 5 to the x equals 5 to the 7th, so x equals 7. Okay, the next question wants us to rewrite our log expression in terms of natural log. Well, the change of base theorem, which is on our formula sheet, says that we can take this log and we can make it log any base. So we'll make it log base e of 4 over log base e of 29. That's what change of base theorem says. You can do any base you want, as long as you stay consistent at the top and the bottom. Now, we don't write log base e, we write that as natural log. So I'll change that to natural log. That's what we want to enter in right there. This next problem is tricky, and I'm not super concerned about it. You can one thing you can do if you can't get these at all, you can graph the left side and the right side, or try it with numbers, like call A1 and B2, and see if it works. There's different tools you have, but it turns out that this is not the same. The first one, because there's a property you have, you can bring down the exponent and make this 2 log base a of b, but that's different. It's not the same as this quantity right here squared. That's a different number, so it turns out the first one's false. Second one, you can bring down this 3b only when it's risen to the power like this, when it's a to the 3b, not when the whole thing's 3b, so that's false as well. Doesn't follow our log properties. This next one is really tough to see. I mean, you can bring this 0.5 up, and there's some different things you can do to try to rewrite it like this. Turns out that's true. If you just evaluate the left of your calculator and the right of your calculator, you get the same thing. So that was true. And then the last one turns out to be true as well. And this one's you can show with log properties. This is really 1/3 on the left side. So if you start with the left side, you can bring this up to the 1/3, and you can bring this down according to our log properties in our formula sheet. And then you can rewrite, because you have a natural log of a product, so you can make this natural log of x plus natural log of y in parentheses times 1/3. So you can rewrite this basically as that. And that's what you have on the right side. So that is true. Yeah, I probably won't ask you a question that tricky, because these two ones that are false are really hard to see, and so is this one. But this one's more doable. The way I'll probably ask this question is I'll start with this, and I'll tell you to expand it as far as you can, in which case you'll rewrite it like that on the right. Okay, the next problem gives you a relationship between the average score in an exam and T in months. So the first question asks, what's the average score of the original exam? The original exam would be T equals 0. So when you plug in T equals 0, you get 95 minus 5 log base 10 of 1. And that's something you can do in your calculator. Just pull up your calculator and do 95 minus 5 times log. You don't need to, this is common log base 10 right there of 1. And that gives us 95. So in the original score, the average score is 95. After 6 months, we're going to plug in 6 right here. So we're basically going to do the same thing in our calculator each time. And we're going to change this number. In this case, 6 plus 1 is 7, so we're going to change this to a 7 in here. Hit enter. That's 90.77. And after 18 months, we plug in 18 for T. plus 1 would be 19, so we're going to do the same thing, but now plug in 19 right here. And that gives us 88.6. Okay, so the next problem wants us to take this log and write an exponential, like this. If we do, it's 8 to the 1/3 equals 2. Like I said, you make a circle, or just remember that a log is an exponent. So when you have the log expression, log base 8 of 2 is equal to 1/3, it's easy to say, okay, here's the log, is the equal sign, and the exponent is here. So the exponent must go here, and obviously the base goes in the base, and which makes 2 go here. So 8 to the 1/3 equals 2, and that way we can say, okay, well, A is 8, B is 1/3, and C is 2. Same thing with the next one, it's 2 to the -5th equals 1/32 if you change it into exponential form. So that makes D2, E -5, and F 1/32. Next problem, once again, change it to exponential, it would be base to the exponent equals the argument. And that's just 2 then. If you're not sure, change 8 into 2 to the 3rd. And then you can compare and see that x is 2. You can also, do that last part in your calculator, but I think it's doable without a calculator in this case. Next one is x squared equals 9. Well, solving this, you can take the square root of both sides, but you do get 3. And you don't want the -1 in this case because we can't have a negative base. All right, the next problem then wants us to rewrite these. Well, I can rewrite this using our natural log properties. This is going to turn into natural log of x plus natural log of y. That's a product property. And so looking for that, that's D. This one I can bring down the exponent and write it as x natural log of y. That's our exponent property, and that's A. This one I can rewrite using log of x minus the log of y, and that's on our formula sheet. That's the quotient property, and that's B. And the last one I can bring down y and write it as still only left with the one C as y natural log of x by just bringing down the exponent. Once again, that's our exponent property. Next problem, you could write this in exponential form. If you call this equal to x, you can do base to the exponent equals the argument, and you can compare and see that x has to be 14. Same thing here, call it equal to x, and you can do 2 to the x equals 16, and you can rewrite 16 as 2 to the 4th power, and so x has to be 4. Same thing, with the last one, call it x, 5 to the x equals 125, but 125 is really 5 cubed, and so x is 3. And same thing with this one, 5 to the x equals 5 to the 7th, so x is 7. Okay, the next problem, if you're going to evaluate this with a calculator using change of base, you can do common log base 10 of 97 over common log base 10 of 4. And the reason you can do that, that's right on the formula sheet. To pull that up in your calculator, then I'll show you that these are equal. I'll do it 2 ways. I'll do log base, so alpha window log base is 5 of log base 4 of 97. Gives you the same thing as you get when you do this, which is common log of 97 divided by common log of 4. Gives you the exact same thing. So, and it wants you to evaluate this to 6 decimal places, so 3.29995